Hello, my name is Tim Harrigan. Today I will present Module 10 of the Appropriate Scale Mechanization for Smallholder Farmers online open course on machinery management. The learning objectives for this module are to understand the following: the importance of machinery management to farm management, fundamentals of systems thinking, how to measure machine capacity, how to improve field efficiency, estimating power requirements, matching tractor size and implements, and managing machinery systems. Owning and operating farm machinery is a major crop and livestock production cost. Machinery-related costs can account for 50% of all annual farm management costs. Machinery management involves selecting, operating, repairing, maintaining, and replacing machinery. Machinery costs can be minimized by selecting the correct size of tractor and implement to accomplish planting and harvest operations within the time available. In some cases, hiring a custom service provider may be the lower cost option, particularly if the crop acreage is insufficient to justify the cost of machine ownership. Machinery management principles will help you estimate owning and operating costs and minimize costs without reducing production. Farming systems are complex. Systems thinking is a problem-solving approach that recognizes the linkages and interdependence of farming operations. Changing one part of an operation can affect the system's behavior. Systems thinking focuses on the relationships between various activities of farming operations. For example, changing tillage equipment can affect soil quality, crop yield, and farm profitability. In forage crop production, the system includes major processes of soil preparation, planting, harvesting, transporting, storing, and feeding in forage. Each stage involves multiple operations and the functioning of many individual components. In systems thinking, boundaries are conceptual limits that define the scope of the system of interest. Boundaries can help define the system's inputs, processes, and outputs. They help identify the components that interact within the system, linkages between system components, and potential external impacts on the system. A sugar beet field harvest operation, for example. The boundary for evaluation of this system may be limited to lifting, gathering, and transporting the beets and tending the beet harvester. In a more comprehensive sugar beet production system, the boundaries may also include tillage, planting, crop care, beet topping, harvest operations, and sugar processing. Machine capacity is a measure of machine performance. The theoretical machine capacity is the performance rate if a machine performs its function 100% of the time at the rated speed using 100% of its rated width without stopping, turning, or other delays. The effective machine capacity, on the other hand, is the actual rate of land or crop processed in a given time based upon the total field time, including turning, overlapping tillage passes, minor machine adjustments, and so on. It is not often possible to operate machines continuously or at their full rated width of operation, so their effective or actual capacity will always be less than their theoretical capacities. A machine can have varying capacities depending on the task. For instance, a grain combine will have a field capacity measured in hectares covered per hour based on the header width and the travel speed. A material capacity measured in kilograms per hour based on the weight of the grain harvested, and a throughput capacity measured in tons per hour of the amount of material handled, including chaff, straw, and weeds entering the header. Field efficiency, expressed as a percentage, is the ratio between the productivity of a machine under field conditions and the theoretical productivity. Activities involving labor and related field operations that should be included when calculating machinery costs are preparation for field time and storage, travel to and from the field, in-field machine preparation time, and operator personal time. Still, these are not usually charged against in-field calculations. Field efficiency accounts for time spent turning the machine, loading and unloading, machine adjustments, refueling, and repairs. In reference to items 1 through 10, field efficiency is the ratio of theoretical field time, number 4, to numbers 4 through 9, the total time spent in the field. Field efficiency varies with the size and shape of the field, the pattern of field operation, crop yield, crop moisture, other crop conditions, and many other factors. Most time lost in the field is turning at row ends, idle travel, material handling, including filling hoppers with seed and fertilizer, unloading harvested crops, clearing clogged equipment, machine adjustment and minor repairs, refueling, and waiting for other machines. Typical field efficiencies for tillage operations range from 80 to 85%, 55 to 70% for planting operations, and 60 to 80% for harvesting and most other operations. Let's consider the example of a disc harrow. How many hectares per hour can one expect to cover with a 3-meter wide disc harrow traveling at 4 kilometers per hour with a field efficiency of 80%? The theoretical field capacity is the product of the machine width in meters multiplied by the travel speed in kilometers per hour divided by 10, a constant. Working through the example, the theoretical machine capacity is 1.2 hectares per hour. The effective field capacity will be less because of time in turning and so on. The effective field capacity is adjusted for field efficiency as 80% of the theoretical field capacity, or 0.96 hectares per hour, 2.36 acres per hour in English units. Let's consider the example of a rice combine harvester. How many hectares per hour will you expect to cover with a self-propelled rice combine harvester with a 2-meter header width traveling at 5 kilometers per hour with a field efficiency of 65%? Using the equation for effective field capacity, we have 2 meters times 5 kilometers per hour times 0.65. Dividing the product by 10, the effective field capacity is 0.65 hectares per hour. This information can help a farmer plan harvest operations or help a custom service provider plan a harvest schedule for multiple farms. What if we move to a different field, long and narrow, that significantly reduces turning time and increases the field efficiency from 65% to 75%? What will be the increase in area covered in an 8-hour workday? Again, using the equation for effective field capacity, we see that the area covered will increase by 0.1 hectare per hour or 0.8 hectare per day increase in productivity. Improving field efficiency can have a significant impact on productivity. Field shape is important. Small, irregularly shaped fields are inefficient for maneuvering machinery, causing many turns and low field efficiency. Long fields and working parallel to the long dimension of the field reduce the number of turns and increase field capacity. Moving around obstructions like stumps and stones reduces field efficiency. Coordinate handling seed and other cropping inputs to minimize waiting time and idle field travel to increase field efficiency. Before going to the field, all equipment in good repair will minimize repair time and increase field efficiency. A well-matched tractor and implement are important in machinery management. Implements that are too large for the tractor power available will overload the tractor, causing excessive tire slippage and tractor breakdowns. Implements that are too small waste fuel and are inefficient. There are usually many implements on the farm, so it is not practical to perfectly match all implements with the power available. A practical approach is to have a good match between the tractor power and the power requirements of the highest draft implements. Most farm tractors are rated according to the maximum power takeoff, PTO, power. A 50 kilowatt tractor can deliver 50 kilowatts at the PTO outlet at the tractor's rear. But drawbar power is transmitted by traction through the tractor drawbar to the implements. A portion of power at the PTO is unavailable for drawbar use in the field because of inefficiency in the tractive surface, causing power losses from rolling resistance and tire slippage. The tractor chassis has a significant effect on tractive efficiency. For example, 2WD refers to a two-wheel drive tractor. In soft soil, only 55% of the power at the PTO is converted to useful drawbar work. The efficiency increases to 64% with a mechanical front-wheel drive, MFWD, 70% with a four-wheel drive, 4WD, and 72% with a tracked vehicle. Now, consider matching an implement with a proper sized tractor. How large a mechanical front-wheel drive tractor is needed to handle a 4-meter wide chisel plow on firm ground at a travel speed of 7 kilometers per hour? The draft of a chisel plow is 6 kilonewtons per meter, and the tractive efficiency is 0.76. First, calculate the implement draft, then calculate the drawbar power needed to pull the implement, and then determine the tractor size needed. The chisel plow draft is 4 meters times 6 kilonewtons per meter, is equal to 24 kilonewtons. The drawbar power is the product of 24 kilonewtons times 7 kilometers per hour divided by a constant 3.6 is equal to 47 kilowatts. For the tractor size, divide 47 kilowatts by the tractive efficiency, 0.76. Multiply the result by 1.2 as a safety factor to prevent overloading and to handle variations in field conditions. The recommended tractor size to match the 4-meter chisel plow is 77 PTO kilowatts. Many farming operations involve the coordination of a system of machines. The goal is to assemble an efficient, smoothly functioning system where no single component limits the system's capacity. Crop harvest is an example of a machinery system whose performance depends on coordinating the harvester, transport vehicles, and unloading operations. Managing system performance is not as easy as managing a single operation, such as tilling a field. The harvester throughput, material transport capacity, and other operations must be synchronized to keep all components moving efficiently. I would like to discuss my work with maize silage harvest as an application of machinery management based on machine capacity and throughput. Rather than matching tractor power and tillage implements, let's see how I matched the silage harvester throughput with the material capacity of transport vehicles, measured as tons per hour. First, a justification for the work. In recent years, dairy farming in the U.S. has changed. The trend was toward fewer but larger operations. Economic realities caused many small farms to leave the dairy business, while others increased their land base and the number of cows. Silage production is a major portion of the cost of milk production, and the greatest cost of silage production is related to machinery. Machinery and labor costs for silage harvesting, hauling, and silo filling range from $130 per hour to more than $500 per hour. When farms were smaller, maize silage was typically harvested with a pull-type forage harvester and transported to upright storage silos in tractor-drawn, self-unloading wagons. Larger farms were now transitioning to self-propelled forage harvesters with truck-mounted dump boxes for transport to bunker silos that may be several kilometers from the crop where the silage was grown. Self-propelled harvesters have an advantage in maneuverability, productivity, crop visibility, and operator comfort. The higher throughput capacity improves the timeliness of harvest, supplies consistent crop maturity and feed quality, and access to the latest technology, such as a kernel processor, to improve feed digestibility. Silage harvest involves parallel machine operations. The harvester harvests and processes the silage. Transport vehicles move the crop material to the storage unit, usually a bunker or upright silo for unloading, and a bunker packing tractor or blower tractor fills the storage structure. A well-matched system runs efficiently with each machine operating with little idle time or delays caused by waiting for other machines to complete their task. Silage harvest involves a system of 2 or more machines performing their job simultaneously. This cycle diagram shows the activities of the whole machine system. The system includes a forage harvester, 2 transport wagons, and a tractor filling and packing the bunker silo. Each transport wagon loads at the harvester, returns to the bunker silo to unload, and then returns to the harvester to repeat the process. The cycle time is the time it takes for each wagon to unload at the harvester, travel and unload at the bunker silo, and return to the harvester for reloading. The manager's goal is to keep the harvester moving. The wagon's material transport capacity must match the harvester's throughput capacity. If the wagon's material transport capacity is too low, the harvester will be idle and non-productive, and the machinery set will be inefficient. A general rule is to have the most expensive machine operating most efficiently. The first stage of evaluating the system was to apply machinery economics to identify machinery-related silage harvest costs. In each figure, the horizontal axis shows the number of cows in the herd ranging from 75 to 1,200. The 75 cow herd used a 1-row forage chopper with 3 self-unloading wagons and an upright silo. The 1,200 cow herd used an 8-row self-propelled forage chopper, 5 15-ton dump trucks, and a large tractor at the bunker silo. The figure on the left is the machinery-related harvest cost in dollars per ton of silage, ranging from $4.25 per ton for the 1,200 cow herd to $8.50 for the small 75 cow herd. The figure on the right is the ownership and operating costs for the harvest system, the harvester, transport vehicles, and storage tractors. Machinery costs range from $132 per hour for the 75 cow herd to $534 per hour for the 1,200 cow herd. Interestingly, even though the machinery costs per hour were much higher for the 1,200 cow herd, the machinery costs per ton of silage stored were twice as high for the 75 cow herd. So feed costs for the smaller herd were significantly greater than for the largest herd. The higher machinery system costs for the 1,200 cow herd were more than offset by the greater productivity and volume of silage harvested. These costs show the importance of the intensity of use on machinery costs. Farmers will use this information to make machinery replacement decisions and decide between machinery ownership, custom hire, or shared ownership. The next part of the work was a motion and time study to determine the time necessary to perform the tasks for each machine. An efficient silage harvest system requires transport capacity to keep the forage harvester moving and forage blowers or packing tractors at the silo to prevent crop flow bottlenecks. The number of vehicles needed varies with transport distance and speed, truck or wagon capacity, the time needed for unloading, and field efficiencies include time in turning, loading and unloading, machine adjustment, maintenance, and in-field repairs. In this work, I evaluated 9 harvest systems on 7 dairy farms with forage harvesters ranging in size from a 2-row pull type to an 8-row self-propelled chopper. Transport vehicle capacity ranged from about 7 to 15 tons with over-the-road hauling distances of 1 to 10 kilometers. Most storage structures were bunker silos. An objective is to match forage chopper throughput capacity, transport vehicle material capacity, and silo material packing capacity so the harvest system works smoothly. The field efficiency of any single machine may be limited by the capacity of other machines or operations. Often, we try to have the most expensive machines operating at the highest efficiency. The forage harvester is usually the most expensive machine when harvesting silage. I measured the cycle times of the forage harvester, transport vehicles, and other essential operations. The forage harvester cycle time included when the crop flowed through the machine, idle time waiting for transport vehicles, and turning and maneuvering on the headlands. Transport vehicle cycle time included the time maneuvering and unloading, time traveling to and the distance to the field, time maneuvering and loading at the chopper, and time on the road returning to storage. The packing tractor material capacity did not affect the cycle time as long as it kept up with the flow of silage into storage. Careful observation of several harvest cycles for each harvest system identified representative machine performance parameters to model or simulate harvest systems with a range of machinery sets, travel distances, etc. A representative chopper throughput was 20 tons per hour per row. The chopper throughput as a percentage of the machine cycle time for field efficiency was 85%. Time spent turning and waiting was 15%. Transport vehicles spent about 7.5 minutes per load unloading and maneuvering in the field and near storage. Average transport vehicle travel speeds were 27 kilometers per hour loaded and 31 kilometers per hour when empty. Trucks average 56 kilometers per hour loaded and 60 kilometers per hour when empty. These performance parameters were used to simulate representative harvest systems. In-field repair time is difficult to predict. Heavily stressed implements, such as tillage tools and complex multi-component machines, have the greatest breakdown probability. Delays for unplugging, replacing shear pins, and so on are fairly common, but difficult to predict. This harvester was down for 45 minutes to unplug the discharge chute and replace shear bolts. Another operator reported expecting 1 hour of daily downtime for repairs and adjustments. Those operating the self-propelled harvesters reported spending from 1/2 to 2 hours at the end of each workday servicing the harvester for the following day's work. A season-long reduction in field efficiency of 10% from 85% to 75% was selected to account for adjustments and repairs, unexpected delays, and moving from field to field. A forage harvester's normal range of field efficiencies is 60 to 85%, with 70% being typical. Accurate estimates of harvester throughput and silage hauling rates are needed to create valid simulations that give meaningful comparisons between system alternatives. The over-the-road travel distance is on the horizontal axis in the figure. 1 mile is equivalent to 1.61 kilometers. I used the identified performance parameters to simulate the harvest capacity of a 3-row pull-type forage harvester loading tractor-drawn self-unloading wagons with material capacities of 6.7 tons over distances from 0 to 11 kilometers. The effective harvester throughput capacity is in red, just under 60 tons per hour. With 3 transport wagons and 2 shuttle tractors with no road travel, the transport capacity was equal to or greater than the chopper throughput, so there was no chopper idle time waiting for a transport wagon. As the hauling distance increased, the transport wagons could not keep up, and the chopper idle time increased. At a hauling distance of 3.2 kilometers, the system capacity dropped from 60 to 40 tons per hour. Transport wagons were increased from 3 to 5 to boost the system capacity to distance fields. 5 wagons kept the chopper moving with a slight delay up to a hauling distance of 4.8 kilometers. In this example, I used the performance parameters to simulate an 8-row self-propelled forage harvester loading truck-drawn dump wagons and a material capacity of 15 tons over distances from 0 to 11 kilometers. The effective harvester throughput is in red, 162 tons per hour. With 4 truck-drawn transport wagons, the transport capacity was equal to the chopper throughput with a 1-mile hauling distance, and there was no idle time waiting for a truck. As the hauling distance increased, 4 trucks could not keep up and the chopper's idle time increased. The system capacity dropped from 162 to 140 tons per hour at a hauling distance of 4.8 kilometers. Adding an additional truck made full use of the chopper throughput up to 4.8 kilometers from the storage bunker with only a small decrease at 6.4 kilometers. This silage harvest example shows how a farm manager and others working with machinery management can use equipment capacity information to estimate costs and select optimal machinery sets to complete field operations within the time available. Summary and conclusions. Farm managers use equipment capacity information to estimate costs and select optimal machinery sets to complete field operations within time, make machinery replacement decisions, and decide between machinery ownership, custom hire, or shared ownership. Systems thinking is a problem-solving approach that recognizes the linkages and interdependence of various farming operations. Theoretical machine capacity is the performance rate if a machine performs its function 100% of the time at the rated speed using 100% of its rated width. Effective machine capacity is the actual rate of land or crop processed in a given time based on the total time in the field. Effective capacity will always be less than the theoretical capacity. Field efficiency as a percent is the ratio of the productivity of a machine under field conditions and the theoretical or maximum capacity. Implements too large for the tractor power available can overload the tractor, causing excessive tire slippage and tractor breakdowns. Implements that are too small waste fuel and are inefficient. A portion of the power at the PTO is unavailable for drawbar use in the field because of inefficiency in the tractive surface, causing power losses from rolling resistance and tire slippage. In a well-matched system, each machine operates with little idle time or delays caused by waiting for other machines to complete their task. A general rule is to have the most expensive machine operating most efficiently.